prepared for the 2021 Astroinformatics Conference. I'm Colin Burke, graduate student at the University of Illinois at Urbana-Champaign, and today I'm happy to be talking to you about my work and work of my collaborators on interpreting the variability characteristic timescale in AGN light curves. So first, just to give a quick introduction to AGN variability for those who aren't familiar, and I should note, first of all, that I'll be focusing in this talk on AGN variability in the optical, but AGNs do typically show variability in other bands as well. But nevertheless, AGN variability is typically well described by a simple stochastic model called the damped random walk. This is not a physically motivated model from first principles necessarily, but it's a model in the statistical sense that is useful for measuring and interpreting the variability and predicting the variability of AGN light curves in the optical. So as I said, AGN variability is stochastic and shows variations on timescales from hours all the way to 2 years and even longer timescales. So on the left here is a figure showing the power spectrum of a damped random walk model that would describe AGN variability. And the characteristic features of a damped random walk is at low frequencies, you have a white noise component, and at higher frequencies, a red noise component. And in between, there's a transition frequency, sometimes called a break frequency, or in my work, I'll refer to that corresponding break timescale as the damping timescale, tau, or tau DRW for tau damped random walk sometimes. But that characteristic timescale is a feature that we can measure using this damped random walk modeling, which I'll go into in a bit more detail later in my talk. So to visualize what this looks like in the time domain, on the right, top right here is a time series showing white noise, which looks like what you might expect. No red noise component in the power spectrum. And on the bottom right is a damped random walk light curve, which looks very similar to what we would see in AGN, in an AGN light curve. You see there's some correlation behavior here, but the light curve is stationary on long enough timescales. It doesn't continue to random walk away. And so that's the flattening to white noise on longer timescales or small frequencies. So that transition between red noise and white noise sets the characteristic timescale in AGN light curves and in the damped random walk model. So that's what I'm interested in interpreting. So this work sort of started actually with a paper collaborators and I did a couple of years ago, looking at the light curve of a dwarf AGN, NGC 4395. So the story behind this is we're interested in TESS light curves. So TESS is a exoplanet satellite orbiting the Earth and getting cadence at 30 minutes cadence. So really high quality light curves. But the caveat to TESS is the light curves, the AGNs need to be bright enough and variable enough to be detected because it's a small telescope. The other caveat is that TESS only observes a certain sector of the sky for about 1 month on average, except for the continuous viewing zones. It rotates around the sky and observes every sector for 1 month. So for that reason, I was interested in looking at AGN light curves on shorter timescales, which has been done before with the Kepler satellite, for instance. But the nice thing about TESS is it's all sky, so it allows us to look at whatever object we want, provided it's bright enough. So we decided to look at NGC 4395. Why? Well, it's a low mass galaxy, and so it's been known anecdotally to have high degree of variability in the optical and also short timescale variability. And it's also very bright. So eye magnitude of around 10. So I thought this would be a great target for TESS. And indeed, what we have here is the test image. The pixels are really big, but using difference imaging, we can extract the flux from the variability. On the right here is the light curve of the AGN in blue and some comparison stars for reference in red. And what we see is that the stars are relatively flat, non-variable, and the AGN shows this beautiful short timescale variability. So we were able to capture this with tests, and we modeled it with a damped random walk on the right and blue. And so this is a light curve modeled with the damped random walk error 1 sigma error ellipse in blue. We also tried a higher order version of the damped random walk called a continuous autoregressive moving average. And anyway, we found that that didn't really improve the fitting for us for this object. So the damped random walk in this case was a sufficient model. And so this is a Gaussian process, which allows us to fit the light curve and infer the time scale using a Bayesian framework, which is really nice. And so it allows us to understand our uncertainties a lot better. So on the left here, I'm showing the characteristic time scale versus the black hole mass. And so on the top right in the magenta data points is the result from previous work of Kelly, 2009. And they say, you can see here that there is a trend with the time scale and the black hole mass, but the dynamic range in this sample is quite small, around 10 to the 8 to 10 to the 9 solar masses. And there's a large uncertainty in the slope and normalization of the tau mass correlation. And furthermore, this work was called into question by the short duration of these light curves and the quality of the light curves. So it's been a little bit controversial in the literature whether this correlation exists or not. Nevertheless, with our high quality NGC 4395 light curve, we were happy to see that given its black hole mass, it falls almost exactly on the extrapolation of the Kelly relation that we would expect. So we would expect to see characteristic variability timescale of just a couple of days in this object, given its low black hole mass being a dwarf AGN. But nevertheless, we wanted to definitively answer the question, is this correlation between the black hole mass and the characteristic timescale real, and does it hold across all supermassive black hole masses? To do this, we constructed 20-year-long light curves, composite light curves from a variety of optical surveys, overlapping with the dark energy survey supernova fields, which have a 7-day roughly cadence, as you can see here, which allows us to constrain the short duration variability. And we added light curves going back all the way to SDSS and ending with ZTF to help constrain the long timescales variability. Of course, in the future, we will have Rubin Observatory, which will allow us to extend the baseline even further for these objects, which will allow us to measure their variability characteristics and the timescale even more accurately, which I'll just go into some of the why we might want to do that at the end of my talk here in a minute. So after constructing this light curve, we restrict these light curves, we restricted to objects with measured black hole masses, mainly from SDSS. So we have SDSS quasars. We also combined it with reverberation mapping monitoring programs, which tends to capture a lot of Seyfert galaxies, which tend to be lower black hole masses, and some dwarf AGNs from the literature using primarily ZTF light curves. Finally, we were careful about only using the highest quality light curves, which have sufficient variability and duration to constrain the damping timescales. And what we find here is our result in the black. So this is the damping timescale again versus black hole mass. And the optical is our result here in the black. We see black data points, we see SDSS quasars over here, which tend to fall similarly to the Kelly points on the previous plot. And Seyfert galaxies tend to the 6 and 7 solar masses, black hole mass, and dwarf galaxies, dwarf AGNs here, which tend to have smaller damping timescales than certainly than quasars. And we found there's a strong correlation across the entire range of supermassive black hole masses, but the slope of this correlation is quite shallow. In particular, we've compared it qualitatively here to the X-ray correlation. And you see that the X-ray damping timescales tend to follow a very different relation, which traces the orbital timescale near the ISCO radius, near the closest point of the black hole. On the other hand, the optical variability has a very different slope and the timescales are much longer. So we think this is a process that's intrinsic to the accretion disk and not a simple reprocessing of X-ray variability. So how can we interpret this timescale a little bit more physically? To do this, we converted our damping timescales in the optical to a characteristic radius in the accretion disk using the standard model of accretion disk theory given by the equation in black at the bottom of the slides. So the plot here is showing the characteristic radius that we're measuring in black data points, and our relation is shown here versus black hole mass in the orange relation with 1 sigma uncertainty. What we can see is that this overlaps well within 1 sigma of the microlensing radii measured in AGNs from Morgan et al. 2018, shown in blue. However, our relation probes the entire range of supermassive black hole masses from 10 to the 4 to 10 to the 10 solar masses, thanks to the large dynamic range of our AGN sample. So this reassures us that the characteristic timescales we're measuring may be intrinsic to the accretion disk and in fact are connected to the black hole mass through the standard model of accretion disks. In contrast, it's possible that the X-ray variability timescales simply traces the ISCO radius near the supermassive black hole. Next, we thought, why stop there? What happens when we look at stellar mass accreting systems and stellar mass accretion disks? To do this, we plotted the damping timescale for white dwarfs from previous work, and these are white dwarfs of the nova-like class, who, like AGNs, their optical variability is thought to come from accretion. And when we plot their damping timescales in the magenta cross symbols here, we found that they lie very close to our relation if you extrapolate it down to stellar mass accretion disks. So our relation here, again, is shown in orange. And for comparison, the blue dashed line is our relation, but with the slope fixed to 1/2, which is the prediction from the standard model of accretion disks. We think this slight 2 sigma or so discrepancy can be easily explained by some subtle selection effects of our measurement, which could perhaps be improved by longer light curves with Rubin Observatory in the future. So this suggests that our relation may in fact be universal for all accretion disks, at least for rapidly accreting accretion disks. And you'll notice the gap in between the dwarf AGNs and the stellar mass accretion disks is the elusive intermediate mass black hole regime. We've yet to find a true accreting intermediate mass black hole. And if you believe that our relation in fact holds down to these masses, then one of the reasons we haven't perhaps found one is their optical variability would be predicted to vary primarily on timescales of hours to tens of hours, less than a day, which would make them very difficult to detect given the typical cadence of at least ground-based surveys. So finally, this suggests that our relation could be a powerful new tool for not only measuring black hole masses using the optical light curves, but potentially for discovery of new dwarf AGNs or low mass AGNs and even intermediate mass black holes where the black hole mass can be difficult, if not impossible to measure with traditional techniques like reverberation mapping or single epoch spectroscopy. For example, if the broadline region produced by the AGN is non-existent or just too weak to detect. For my final slide, I'll demonstrate what a predicted light curve of an intermediate mass black hole might in fact look like with an eye towards, say, Rubin Observatory. So on the bottom left here, I'm showing a simulated light curve of an intermediate mass black hole with a black hole mass of roughly 10 to the 3 solar masses. And our Gaussian process damped random walk model is fit to the simulated light curve in orange. On the right is the posterior probability distribution of the inferred characteristic timescales from the time series Gaussian process modeling. And on the bottom, or excuse me, on the top scale here, axis of the right-hand side of the figure, is the corresponding black hole mass using our relation constructed using AGNs. And what we can see is that we can well constrain the mass of an intermediate mass black hole if we have a light curve of at least 30 days with sufficient cadence that is smaller than the damping timescale that we're trying to measure. So in this case, the damping timescale of an intermediate mass black hole is predicted to be a few tens of hours, less than a day. So it would be great to have a high cadence mini survey, perhaps, to use that as an opportunity to conduct a search and to do mass estimation for potentially for intermediate mass black holes. So this simulated light curve here has a 2-hour cadence and really demonstrates, I think, that Gaussian processes can be a powerful tool for not only modeling AGN variability, but to hopefully interpret their variability properties and potentially in the future to discover new dwarf AGNs or potentially intermediate mass black holes with a high enough cadence to allow us to actually sample the light curve sufficiently to measure the damping timescale. And finally, I'll say that we can look at really the smallest dwarf galaxies. There's been some recent work searching for intermediate mass black holes and dwarf galaxies, which have come to promising results. And so for an intermediate mass black hole, we should target our search to the smallest dwarf galaxies using a high cadence monitoring program to robustly measure their black hole masses before we can do other follow-up observations. So thank you for your time, and please follow up with any questions you might have.